Hello everyone, I'm Yifan Wu from Group 5. My QMUL ID is 231222534. I'm the main demonstrator for this lab session.
Hello teacher, my name is Zhang Jun and my student number is 23122235.
Hello, my name is Anthony. My student ID is 231220367.
Hello, teacher. My name is Zhang Yunhe. My student's number is 231221205.
My name is Wang Zaiyu, and my student ID is 231222464.
Here's our 4-bit multiplier design, and we didn't use the multiplication symbol. Instead, we built it from scratch using an array structure. And first, we generate the partial products by using an AND gate, and then we use this row of 4 adders to sum everything up, step by step. And we use 3 keys to verify our test bench. And in our test bench, we can see that we use a loop to check every single combination, and we can see the outcome is correct. So it's proving that our adder array works perfectly. This is the test bench for our ripple carrier subtractor, and we tested 3 scenarios to verify the logic. The first one is 10 minus 3, and we have a positive result, so the count should stay high, and the result is correct. And second is a simple zero check, and the outcome is also correct. And the third is 3 minus 10, which has a negative result. So we expected the count drop to 0, and the signal has a borrow in hardware logic, and the outcome also verify our logic. Here's the test bench for our prime finder, and we have used the signals such as dividend divisor and load to help us verify our outcome. And we has used set the input to 7 divided by 2, and when we post the load signal high, and after it stabilized, we can see our output from hex 0 and hex 4. And hex 0 is 10110000 and equals the decimal number 3, and the hex 4 equals decimal number 1. So the outcome is correct, so we successfully verify our prime finder. Here's our test bench for division model, and we make the divider uses a state machine, and we first generate a clock signal here, and we tested 3 scenarios, which are 13 divided by 3, and 12 divided by 4, and 2 divided by 5. And from our test bench, we can see all of the scenarios are totally correct, which verify our outcome.
So we have already downloaded our design to the board. SW9 is the light of showing it is a prime number or not. From switch 7 to switch 4 is the dividend, and from switch 3 to switch 0 is the divided. Let's to test 7 is the prime number or not. We have to target this up. And let's start from 2, test from 2. Load up and down. You can say the quantity is 3 and the remainder is 1. And let's try 3. You can say the quantity is 2 and the remainder is 1, which is correct. And let's try 5. You can say the quantity is 1 and the remainder is 2, because the remainder will not be 0, so the light still went on, so it is a prime number. And if I switch the dividend to 8, and I divide it by 2, you see, the remainder becomes 0, and the light went off, so it is not a prime number. Design by using the simulation. So if we change the dividend to 7, and we test the divisor from 2, you can see after we load it, the hex 0, which is the quantities, and hex 4, which is the remainder change for what we have we desired, which is 3 and 1. And we also test 7 divided by 3, which generate result that we wanted. Also, we have tested 8 divided by 2, which said that the remainder is 0.
Hello, teacher. I'm Zhang Yunhe. I will introduce the logic design of the prime finder system, and I will explain the code from top to down. First, let's look at the top level entity, prime finder group 5. The field manages the physical board resources. It uses the 15 mHz clock and 10 switches for input. Switch 3 down to 0 are the divisor, and the switch 7 down to 4 are the dividend. Switch 9 acts as the load signals. For output, it controls the LEDs and the 7-segment hex displays. Now let's look at the core logic. The model instance shows the calculation core named long division 4-bit group 5, mapping the switches and to the dividend and the divisor input. The prime check. This is a simple but crucial logic here. If the remainder is not equals to 0, the signal internal is prime goes high. The signal lights up to LED R9 to indicate the result. Finally, it uses a function called 7 decode to convert the binary quotient and the remainder into partners for the 7-segment displays. And now let's look at the core divider architecture. It controls two internal components, its multiplier and the subtractor. It uses a state type definition with the three states, IDLE, CALC, and down. The algorithm in calculate states, the system uses a trial quotient method. It takes a counter Q quant, multiply it by the divisor to get a product. It then checks, is the product greater than the dividend? It determines this by checking if the upper bits of the multiplication results are non-zero, or if the subtractor generates a borrow. If it overshoots, it means the previous Q quant was the correct answer. The system captures the value and moves to down state. If it fits, it's up to the valid quotient and the remainder increment Q quant and tries again in the next clock cycle. Now let's look at the arithmetic unit. The multiplier unit. It used the structure architecture. First, it generates partial products using nets loop to AND every bit of the input A with every bit of the input B. Then it sums these partial products using 3 rows of cascading 4 adders, switching these bits a property to produce the final 8-bit product. Now let's look at the subtractor, this one. And to calculate A minus B, it actually inverts the input to create B. It sets the initial carry in bits to 1. Finally, it uses 4 adders to generate the difference and the carry out. Finally, let's arrive at the foundation block of the design. This one, 4-adder group 5. This is the standard 1-bit 4-adder used repeatedly in multiplier and subtractor. The sum is calculated using XOR gate. The carry out is determined by checking if any two inputs are high, using add or and OR logic. The 2-bit AND gate, it is a simple useful. It takes 2 single-bit inputs and outputs their logical AND. While simple, it demonstrates the model approach of the product. To summarize, Group 5 design demonstrated a clear hierarchy. It's built from basic logic gate to 4-adder, combines those into arithmetic units, coordinated them with the state machine for division, and wraps everything in a top-level interface for user.
Hello teacher, I'm Wu Yifan and I'm responsible for the phase 2 implementation of this design. First, I will download my design to the board. Okay, download correct. We have 2 functions for this design. The first one is a standard prime funder, which allows you to enter a 6-bit decimal number through these 2 keys, key 0 and key 1. Pressing key 0 would allow toggle on this bit, and pressing key 1 would switch the bits that is toggled. Let me show you. If I want to enter 100013, I will say key 1, this is the most significant bit, 2nd bit, 3rd bit, 4th bit, 5th bit, and the last bit, I will change it to 3. If I press key 1 again, it will show you that it is a prime number because it is. LED 0 will on, saying that it's a prime number. If I change it to, let's say, 90013, it can be divided by 3, and so it is not a prime number. So let me just show this. Say it is not a prime number. Because the LED 0 is not. Okay. For the second function, we have created a auto finder for prime number. If you enter number, it will auto display all the prime numbers that are smaller than the number you have entered. Let me show you. let's say 0, 0, 0. If I want to find all the prime numbers that are smaller than 303, and I would just, that is, see, it auto display all the prime numbers that is smaller than 303. And LED 9 is also saying that it have already finished calculation. And if I toggle SW1 and SW2 on, I can change the speed of the rolling. Let's try it again. See, it is rolling much smaller, about let's say 2 minutes a number. Our top level entity is the prime finder is entered, and prime core is the core entity for our to determine if the input is a prime number or not. We have made some improvements. First, an even number that it could be divided by 2 would never be a prime number. So we just skip this and we do not check it. If we say if that is divided by 2, could be divided by 2, then we just said this is not a prime number, and we will finish the loop and just do not let it enter the calculation loop. And if the input number is a even number, then we'll just divide it to its square, which will largely reduce the number of the amount of calculation. And our top level entity is the prime finder, which is a finite state machine. We have all these port definitions here, and we have a series of states here, and we just jump to the state machine. That is the set and logic. If we set all the numbers, we will jump to the decide mode, which decide if we are using a single mode to determine this is a logic. It is a prime number, or to list all the prime number that is smaller than the number you have input. The reason we could calculate a 6-bit decimal number is that we are implementing a 32-bit calculator using the numeric library. It is a default 32-bit calculator, and this is all the calculation design which uses the prime core as an entity. And the auto list is also to count the number to test it if it is a prime or not. If it is a prime number, it will be displayed. If not, then we test the next number until you reach the limit of our core logic of determining if a number is a prime or not. We're trying to illustrate that by eliminating some numbers from our calculation, we are able to save time when calculate if a number is a prime or not. For example, 13s, we have only to wait for 10 clock cycles before reaching our result. And for 121, we have also about 20 clock cycles, which is far more short than it originally supposed to be. It is much time efficient.